we cannot stick a temperature sensor in, and we need to know the temperature.
But now it's pretty sexy to also do it with AI.
Especially, we are training on pure data. The domain knowledge is not exactly necessary. So therefore, even if the neural network is in a range where it's not really 100% sure, or it hasn't been trained, it will still give a reasonable output.
This TNN can also be very bogus if you have, for instance, only maybe one temperature.
But if you place all the three sensors on one mass and forget about the other masses, then of course the three sensors are giving very similar results.
All right, super excited for a new podcast episode today. It's all about thermal neural networks for temperature modeling in e-motors. And I'm very excited to have two specialists on the show today, namely Tobias and Georg. Welcome.
Hello.
Hello. Hello.
So it's going to be really exciting because thermal models also work in a classical approach, so you can solve them analytically or some other methods, right? And today we'll talk about the fancy side of solving equations, which is artificial intelligence. And Tobias and Georg, you will explain us how that actually works with the example of thermal neural networks, short TNNs. So maybe to begin with, maybe Georg, you can start answering the question: why do we need thermal neural networks to begin with? What's the problem that we're trying to solve?
Say the problem we are trying to solve is we have an e-motor and we cannot stick a temperature sensor in, and we need to know the temperature simply because above a certain temperature the magnets will demagnetize and you don't get anymore the full power of the e-motor. Therefore, we have to protect the e-motor, and very good temperature knowledge is important for the lifetime.
This is very well summarized. Tobias, anything that's missing, or do you think Georg answered it in the perfect way?
No, I think he answered it quite well. Yeah. So having this accurate temperature knowledge is really important for safe and also efficient operation. Yeah, and you just don't want to stick a sensor there.
Yeah, that makes complete sense. Yeah, go ahead, Tobias.
Yeah, and therefore you need somehow this somehow virtual sensing. And as you were pointing out, it has been done, let's say, in the more traditional way, but now it's pretty sexy to also do it with AI.
Mm-hmm. So the question is, obviously, you could probably simulate it using some kind of simulation model, which probably the problem is you cannot fit it on an ECU, right? So the approach that you guys are taking is using artificial intelligence, if I'm not mistaken, but please correct me if I'm wrong. So what makes it so, as Tobias said, makes it so sexy to use artificial intelligence for thermal modeling?
Yeah, I can say it's not a complete artificial intelligence model alone. It's already a kind of hybrid model that combines already somehow physics and engineering know-how on the one hand side, with somehow machine learning. And the kind of model that we have here is a kind of model which you can say is called maybe embedded physics model. So you have a kind of a physics engine that has been developed over the past, at least the overall framework. It just lacks a couple of parameters that you need to adjust to your system. And only those parameters you adjust basically with machine learning. And once you have them, you just plug them into your physics engine. And in that form, you nowadays try to approach this problem.
Mm-hmm. What is the promising bit of thermal neural networks? Maybe Georg, you wanted to say something. Go ahead.
Promising thing is simply that we, with this hybrid approach, we have a smaller network, which is and an interpretable network that we can safeguard it, and we have a continuous outcome, which is also not clear from a black box model. And especially, we are training on pure data. The domain knowledge is not exactly necessary, and therefore we can scale it up to also other applications. Even the power electronic units we can apply with that. But we don't necessarily need to know the geometry of this kind of stuff. And the important thing is here, we get a very high accuracy. And with the high accuracy, we can have a higher availability of the high power of the e-motor, simply because if you want to avoid 140 degrees C, exceeding 140 degrees C, and you have an estimation which is accurate to 20 degrees C only, you have to cut torque or the power already at 120 degrees C. If you have it accurate up to 5 degrees C, you can go up to 135.
Mm-hmm. That makes sense. You mentioned one very important thing, Georg, which is the interpretability. So going from a black box approach to a white box approach. I think it would be very interesting for the engineers listening to this podcast. How is it interpretable? Like, how would an engineer be able to interpret what's being decided by a neural network?
Say this thermal neural network, it consists of 3 classes of neural nets. These are the power inputs, and then the conductances, which are essentially the heat flow between the thermal sensors, and also the thermal capacitance, which is more or less or thermal mass of the LAMP parameter model. Essentially, you have assigned to each of the sensors, you have assigned a mass, and which describes how much energy is needed to increase the temperature by 1 Kelvin. And this is these quantities are physical quantities, and they have a certain range, and so you can directly map this and also limit it. So therefore, even if the neural network is in a range where it's not really 100% sure, it hasn't been trained, it will still give a reasonable output, say.
Got it, understood. Tobias, one question for you, maybe in terms of the accuracy, right? I mean, Georg gave us a couple of examples with the temperature range of like 20% of 5C, or 20C in terms of accuracy. What accuracy can we expect using TNNs?
I think it's hard to say it on a, let's say, general temperature range, because I mean it also depends also on the precise e-motor. But I mean, in our case, where we applied, and also in the case, for instance, where the original author of this technique, so researchers from University of Paderborn, it always beats, let's say, all of the other methods in terms of let's say overall temperature accuracy, or also in things like worst or max error metric, for instance. Yeah. So in general, basically, they have really excellent temperature predictions or temperature prediction capabilities. These kind of models.
Understood. I think it would be also very interesting from a fundamental principle how these thermal neural networks are built, right? And there's something called lump parameter thermal networks, LPTNs. Very hard acronym. So can you explain, like, where does it come from and why is it so promising that we use these LPTNs?
I mean, I can say, so these lump parameter thermal networks is precisely this embedded physics engine I was talking about before. These lump parameter models, you can see that they are in some sense a kind of idealized version of your physical system, in that you just consider certain regions, and in these regions you associate certain parameters to it that describe somehow the effects you're interested in, how it also maybe interacts basically with other regions, but what happens then within these regions you don't care anymore. Yeah? And this lump parameter thermal network is precisely such a model where effectively you have such regions, where in each region you associate such parameters like what is a thermal capacitance, what are maybe power losses occurring basically in this unit, and also what are maybe thermal conductances to somehow model the heat flow between this region and neighboring heat such regions. Yeah.
Yeah, in principle, we could see this see this from 2 sides. The one thing is that in the classical or traditional engineering approach, you have a very high dimensional state space called, where you have about 100,000 of masses, small masses, solving the diffusion equation very accurately. However, this is by far too big to bring it to a control unit, of course. And so therefore you squeeze it. You can try also with matrix operations to squeeze this down. And this leads also to a sort of lump parameter model, because also you have regions with high conductance and regions with low conductance, such that you also build up some sort of effective lumped parameters. But the problem there is you have only the possibilities to interact linearly in this kind of model order reduction. and therefore you still have higher dimensions or higher number of masses which you have to interact. And on the other hand, coming from the lump parameter models, or if you have just a few mass models, you have just effective parameters, but you could interact non-linearly. And this nonlinear interaction between the masses could be explained by or described by neural networks. And so therefore we are essentially in the optimum between the both worlds. If you wish, high dimensional linear or non-linear and time dependent. And this is somewhat the sweet spot, if you want, where we are acting.
Yeah, maybe a redundant question. Maybe you guys, Tobias and Georg, you can answer it for me. I had a couple of guests on the show already talking about physics-informed neural networks. Is the TNN any different from physics-informed neural network from a mathematical perspective, or is it very similar or much, much different?
It's different. So if you have somehow let's say that this, if you consider that you want to bring certain physical information or prior into the neural network, you have a couple of different methods that you can use. And one option is maybe physics-informed neural network, which traditionally basically you just add a certain loss term to your loss function, that certain constraints are supposed to be satisfied. But here we have more precisely this stuff, as I was trying to tell, with this physics engine. Yeah, you have some of this physics engine and you just estimate, let's say, parameters before that. Once you have them, you plug them into the physics engine. And the thing I always like to compare it to is maybe an example which people can associate even easier is the case that you have maybe the example that you want to estimate where a ball that you throw is going to. And we all know somehow these idealized projectile equations. And what you do maybe in this embedded physics approach is that maybe from the first few observations that you maybe get, you estimate something like what is the initial position, what is the initial velocity, and once you have them, you just plug them into this idealized projectile equation and can further compute where the ball is thrown to. And maybe you even estimate a few other parameters. Maybe you even estimate the gravitational acceleration, because we know in the ideal case, basically, or let's say on our world, basically these are just idealized equations and they don't fit precisely, but maybe it fits better with a slightly other gravitational acceleration due to effects like random winds whatsoever. So in that form, it differs.
I have another question in terms of the idealization of the equation that we're trying to mimic. How well does the model generalize? Let's say we trained the TNN on one e-motor. How well does it apply to another e-motor, or does its TNN have to be trained on that specific motor data, so to speak?
So in principle, you have to learn on the new motor as well, but it learns, of course, quite faster than a black box model, which has to be trained on every detail on every working point. So it's way faster to train, and it's more or less, as I said, scalable, because you just need the data, and and it's more also extrapolatable, what we call it. Say if we have points close by, so they can interpolate between two temperature which has been seen before, and even to working points which not have even be learned before, if you still get say a decent result. So therefore, you can choose, say, by what kind of accuracy you want. You can choose how many tests essentially you have to take. And we can do this even beforehand. Say we do this in some kind of virtual rig, that we train the data on the development model before, that it trains essentially the principal behavior, but the real behavior needs to be trained on the real sample then afterwards, in some sort of transfer learning process.
Got it. Okay, understood. So you mentioned a couple of things now during the podcast in the first 50 minutes. We have the physical interpretability, which is great. It's end-to-end trainable. And what's also very fascinating, Tobias and Georg, what you're working on is it's kind of, if I'm not mistaken, kind of independent from the material and geometry specs of the e-motor. Is that accurate?
Yes, you don't need to put that much prior knowledge into how these different regions are connected with each other. So effectively, which usually requires also a certain domain knowledge, but you can start that you assume that every region is connected with everything. Then you let it train, and later, since you can look into how are the conductances performing over time, you can roughly also see, are these large conductances now between these two elements or small conductances, and whether this, for instance, also fits to my rough understanding of the geometry. So this is some very good thing that you later can look into it, how it would best fit my data, and does this also match my rough understanding. And if you by some means know that maybe this is not connected with this, then you can also, of course, enter this directly into the system. So this is one great advantage there.
Mm-hmm. Georg, you mentioned the topic of transfer learning. Would that mean I could take a thermal neural network for example, for e-motors, but I could in principle also apply to any other domain or something that has to do something with thermal neural networks? For example, it doesn't have to be an e-motor, it could be any other component. Does it work like that?
Yes, but I wouldn't call, in that case, I wouldn't call it transfer learning. Transfer learning for me, it is a pre-trained network which has the same topology, say, and you just do a refinement, say end of line, or just some particular cases if you want to fine tune the low temperature behavior or so. This I would call transfer learning. If you change to, for example, a power electronic unit, you have completely different time scales. For example, the bus bars are different from the power units that they behave. The power units are much faster. So therefore, you need to have you need to start from, I don't say from scratch, but with a new set of sensors. In that case.
Got it. Understood. Okay. Yeah, that makes sense. Another question I have is, I saw the GitHub repository, so I see there's a lot of MATLAB code involved. So we'll talk about the implementation right now. Why MATLAB, and why not another piece of software, or like maybe some other kind of language? Why MATLAB?
Okay, I can say this was a very important point for us, because I mean the authors who proposed the thermal neural network, they made already some reference implementation in Python PyTorch, and Python TensorFlow. And in Schaeffler, lots of engineers are using MATLAB, and therefore it was, of course, very important for us that we also deliver and translate this tool also to MATLAB. And on this, I'm really happy that we had a good collaboration with MassWorks, and that we were also able finally to also open source this piece of code. So at the moment, you can find the MATLAB implementation of the original example in the paper introducing the thermal neural network. You can also find now the MATLAB implementation. And this is something that I'm really happy that we could do it, and also in this repository.
And on top of this, of course, we also use the MATLAB say process from say model-based system engineering down to autocode generation, and therefore this piece of artificial intelligence really fits perfectly into this given process, such that we don't need to go over to a different tooling, and we can directly create code or use it in SIL, MIL, or HIL environment.
Okay, this is interesting. So in the podcast, we kind of took a top-down approach. We talked about the general problems, how to solve them using TNNs, why they're important, talking about the specific language, which is MATLAB as an implementation language. And I think now it would be really interesting to delve a little bit deeper into the architecture of TNNs. So maybe, Tobias, if you want to get started, how do these TNNs actually work? Like, where do we begin with in terms of the equations, et cetera, et cetera?
Yeah, as said, so in this TNN, it rests basically on this lump parameter thermal network, which in some sense models these two effects that in a certain region, the temperature in one time step can change due to a power loss contribution, so that heat is just produced in it, or that somehow the heat flows to one of the neighboring regions. For that, you have somehow a very specific update equation on the temperature change then that involves somehow these critical coefficients or parameters that I was telling before, and those you just estimate with your neural nets. And once you have them, you can stitch it together in this equation to calculate some temperature change. And this is basically then the temperature change that you apply to your running temperature estimate. So summarizing once more, it's like this: you initialize your temperatures, you always use these neural nets to estimate what are the power losses, what are the conductances, maybe also what are these capacitances, and basically once you have them, you just plug them in this update equation.
Yeah, that makes sense. I have one question. There's a lot of benefits into your approach that you talked about, right? TNNs, Tobias and Georg. What would be some of the disadvantages? When does a TNN fail, so to speak? When should you not use a TNN?
There has been some further research, for instance, from people, for instance, in Volkswagen or also in Aachen, who somehow, I mean, this TNN can also be very bogus if you have, for instance, only maybe one temperature. If you have only one temperature you're interested in, then effectively you're just having one temperature region. You're not having another one. So you're not even having this process that the heat can flow off to something else. So you're only having this power loss. And the only thing that can happen, it can heat up. So in that sense, basically the model grossly underfits. So basically the model has a very low capacity. And of course, you can somehow enlarge again the capacity of the model by assuming that you know that there are also some virtual regions or virtual temperature nodes to which maybe the heat can flow to. You don't get some direct observations, basically what are the temperatures of these, but you can still get some indirect feedback by looking at the temperature or at the spots you're interested in, simply because you see that the heat flows off, or and this is a very important, let's say, extension that still is, I think, under investigation.
Yeah, and very simply, the shortcoming essentially I see is you have you predict some temperatures, and the question is where are these temperatures? Say you can set the temperature sensors and at some reasonable places where you have the big masses. Say if you have 3 masses and you place the sensors on the 3 masses, then it's good. But if you place all the 3 sensors on one mass and forget about the other masses, then of course the 3 sensors are giving very similar results, and you don't have any linkage to the other relevant masses. So in principle, you need to introduce, you need to have a certain physical knowledge about the system before. And I think this is pretty much fits also to what I said before. You cannot do transfer learning directly from an e-motor to a power electronic unit. If you change it to a complete new system, you need to set it up somehow, but without, say, more or less the general topology and not the geometry, as you said, and not a particular geometry. But once you have set it up, you can scale it to all other applications.
Mm-hmm. Maybe I've asked the question already, Tobias and Georg, but maybe I'll phrase it differently. How would you actually, as a practitioner of the TNNs, when maybe you're working on a test bench, appropriately collect the data to be able to feed it into the neural network? Is there a specific format you guys need or this TNN need? How would you actually advise the practitioners to use TNNs if they are already collecting data, if you get my question?
Yeah, so you didn't ask the question before. And actually, basically, it's always a very difficult question. Which data should you collect for the purpose in training this AI model? And this is something I would say is still under research. What are the best scenarios you should collect there? Because in some sense, it should be, of course, scenarios on which you also later want to apply basically this temperature estimation. Yeah. So these and we have, for instance, used very have used, for instance, a mix of, let's say, very classic test rig measurements that one is conducting there. and also simulating certain driving cycles, let's say certain standardized driving cycles like this WLTC driving cycles. Yeah. But of course, ideally, it should cover somehow the space where you also want to employ basically this model. And of course, it has some further extrapolation capabilities. But of course, at some point, if it is too far away, then still there are always some issues. Yeah? And then you are somehow missing the data.
And that's exactly the reason why we are using this virtual rig before, where we can test essentially, say what is needed, what kind of use cases or cycles do we need to consider in order to be sure that the temperature is sufficiently accurate. Say in that case, you just used, as I said, we just used the development model and train the thermal neural network and just compare to the development model, okay, what kind of accuracy compared to the development model we can reach and what kind of tests we have to do.
Understood. I have a maybe very important question, which is always the discussion between interdisciplinary or like in an interdisciplinary topic such as TNNs, where you need the domain expertise of a machine learning expert and the domain expertise of the engineers. You need know-how on both sides. How do you actually communicate in such a way that one understands the other?
Yeah, it simply takes time that basically both understand the language from the other. Yeah? And I think this is a primary example here. I mean, I'm a data scientist, basically. I don't have much background on the temperature modeling, and Georg is in some sense from the other side. Yeah? And basically, on this one first has to gain an overall understanding basically of what one is trying to do here in the middle, and what is this combined approach, and what are the pro and cons basically from both sides. Yeah?
Frankly speaking, I see this as a very good example that people can come together and discuss, and eventually we find a common language.
Yeah, that makes sense. Any other use cases that we can talk about apart from e-motors? I think you've also presented on the MATLAB Expo, or is it still coming?
It is coming, basically. It is recorded and it will be displayed basically on the 13th of November. So if this podcast comes out before that, so you can still register and have a look.
Excellent. Is there any other use cases you guys can or want to talk about apart from e-motors where TNNs apply?
I'm not sure. I mean, we can maybe say that we applied currently to power electronics, as Georg was pointing out.
As we meant, you can apply it essentially to all thermal system you can think of, and of course the next one would be battery or even interior from the cabin or complete vehicle. And but this is right now just in progress. So in principle, there is no limitation if you want. Say if it might be, if it's getting too complex, it might be that, and especially we said this thermal neural network is important for if you want to have a small neural network which is deployed on a control unit. So therefore, for the complete vehicle, this will not be modeled in the control unit. So therefore, the limitation is not with regard to the system. It's rather to what it's used for.
Okay, understood. Got it. Talking about limits, Georg, I think this is a very good segue into the amount of limited parameters, right? I think there's a specific amount of parameters that we use in kind of this model. Like, why is it a limit, and what is the actual limit, and why do we have that limit to begin with?
I don't say there is a limit. Say if you use it on a high performance controlling unit, or if you have unlimited say capacity available, that there is not a limitation of the parameters. Of course, if you want to deploy it in an embedded controller where you have just limited capacity, you have to look around and what is possible, and there is say you should end up say between a few hundred or a few thousand parameters maximum. Otherwise, you cannot get it to the controller. And and of course, it also scales with the number of temperatures you want to estimate.
Anything else you would add here, Tobias?
No, I think it's always this trade-off. How big is the ECU? How much space you have? How much performance do you also require? Basically, and then you can very easily tune there also the parameters.
If people want to get started using TNNs, I mean, we mentioned the GitHub repository, one archive paper. I think I can also link in the description. Anything else? Whatever you would advise people to advise if they want to get started using TNNs?
You can say basically the MATLAB implementation, you can just go on the repository. Basically, there's in one folder the MATLAB implementation. Just download it. It also directly downloads you the data set for this example via the MathWorks file exchange automatically, so you don't even need to get it somewhere else. You should have a new version of MATLAB installed, so preferable 2025. And then you can directly run this example. It runs basically as fast as the Python variants there. And basically it runs just on a CPU. So there's no GPU involved here, because on the GPU it's even slower, the model there to train. And you can give it a try. And of course, if you want to employ it for maybe your precise e-motor and so on, of course you have to touch a bit basically the way how the data is prepared, provisioned, how you make maybe a training test split whatsoever. These are stuff you need to do yourself.
Interesting, cool. Is there any question I didn't ask you in this podcast that you think might have been relevant? Anything that we missed, Tobias and Georg?
Maybe one thing that we can still stress once more are all the advantages of the TNN. Because I think on a high level, I can say maybe, of course, you have these excellent temperature predictions. You have some of this interpretability. On this interpretability, you can also say, I mean, we said that you can check some of the geometry, but you can also say, you know basically also how the model behaves. So you have certain features built in. So you know with power losses, the system can never cool down, or that, for instance, also temperature in this heat flow is never flowing in the wrong direction. Which is usually very hard to ensure in a complete data-driven approach that these properties are even satisfied. There is the advantage that we know also how to initialize the system. So when you switch on the e-motor, you have to start with what are your initial estimates, and when you do certain errors there, you have here a behavior which is very robust to initialization errors, which is a great feature. I mean, that the models are pretty small. I mean, we mentioned already. I think you can also run it on a different, let's say, sample time. So if you record, like in our case, 1 second data, and you later apply it only on 2 second data, then you can still do it, because you have such a sampling parameter in this update equation that you just need to change. And this is maybe also a great advantage if you want to also apply it maybe to some async scenario.
No, I think these advantages which you mentioned, they are definitely there and worth mentioning. And I think the interpretability maybe also lead to to easy to safeguard the model, such that we can use it even in functional safety relevant parts. So this is also a big advantage compared to the complete black box model, because there you can just limit, say, okay, the temperature is in this range, and then it can jump up or down, can have spikes. And this, the result here is definitely a kind of smooth, because we just determine, say, the delta of each time step. So therefore, we definitely have some sort of smooth behavior, which always lead to a convergence to finite temperature, and also finite temperature change during one time step. So that's a very big improvement.
Cool. All right. Anything else that you will expect for the future in terms of TNNs? Is there any research? I mean, Tobias, you mentioned a couple of things that are still under development or research. Anything else that people can expect in the coming years, maybe months, in terms of TNN research? What's coming?
I think the approach basically that has been taken in this paper, that you in some sense have such a state space model, and you effectively model with your neural networks some of the first derivative of, or the state space dynamics. I think this will be applicable to many other scenarios, and most likely has been already applied in certain other cases. And I think on that you have quite some research, I think, and applications coming up in my opinion.
Right. I think if there's nothing else, I think we pretty much covered everything. As I promised, I will put every link to research, code bases, etc., in the description so people can check it out, get started, and use MATLAB. I'm a big MATLAB fan myself, so I'll probably also use it myself in the coming days or weeks. Thank you very much, Tobias and Georg, and I'll also put a link to your contact data in the description so people can reach out to you if they have any more questions. Thank you very much, and I'll hopefully see you in the future for another episode of TNNs.